Hey, welcome to lecture 2.2. This is matching up with section 2.2 in the textbook on volumes. We're going to do a few things in this section. We've built some intuition so far on how to find the area between two curves. Hopefully that was a warm-up or review on what you learned in Calc 1, how to find the area under a single curve, and you might have even learned area between two curves. Depending on the Calc 1 professor you had or when you took it, maybe it was a high school BC class, you might have already learned some ways of finding volumes, namely how to find volumes of objects that are obtained by rotating some region around an axis in the XY plane. What we're going to do is take a step back before learning how to rotate and try to build up some intuition for finding volumes of any object that we can orient in the XY plane a certain way, and then build out a 3D volume from it. So the name of the game here is cross sections. We'll first talk about dimension and volume in general, and then we'll start talking about cross sections of an object. Then we're going to find out how to convert the area. We'll need to write down the area formula for a cross section, and those should be geometric formulas we're used to working with. But the next step will be to write down that area, and then thirdly, to convert it into the volume of a solid, having those cross sections. Finally, we will have some visualizations today. Some of it comes from our intuitions about area and area between or under curves. And some of it will come from some new intuition we're building today on how to draw a region, an area, and then build it out into a three-dimensional solid, having those cross sections as the region or as the original area. Well, along the way, a special case of this will be volumes of solids of revolution, which you might have seen before. And again, it's okay if you haven't seen this in Calc 1. This is a good place to start on this topic. So let's jump right in. And first talk about what volume is. We've been doing area so far in this class, in our one lecture so far. Volume is a similar notion, and I want to set this up in a way that can generalize to even higher dimensions if we need that eventually. So in math, definitions are really crucial ingredients in a lot of these classes. And I believe this is the first definition we've had in these lectures. I'll put it in quotes, we'll sort of define the dimension of an object to be the number of degrees of freedom available to a point traveling within the object. This is kind of a fuzzy definition. What does it mean to be able to travel, for a point to be able to travel in the object? What do degrees of freedom mean? We're not going to specify this any further than this, but you should think of the definition as telling you how many logical different paths you can take that are independent of each other inside of the object. If you pick any point in that object, in that region, let's say, sometimes you can only travel in one direction and its opposite. We'll call that one dimension. And for example, example 2 on this list on the bottom of the slide is a circle. A circle lives in, we usually think of a circle as living in the XY plane. So it lives in a two-dimensional world. But it's actually a one-dimensional object itself. If you pick any point on the circle and try to travel along the circle in either direction, you can only really travel two directions, but they're really the same direction. You can travel clockwise, or you can travel its opposite counterclockwise. We'll call opposite pairs of directions like that the same dimension. So that's a one-dimensional circle. Notice that if you pick any other direction to travel other than that single direction or its opposite, you leave the circle and you're off into the plane into a different direction. The plane itself, the XY plane, is two-dimensional because you can travel up and down. You can travel left and right. To get anywhere else in the plane, you can combine these two, travel to the right by a few units, and then travel down. That's the same as traveling diagonally into the fourth quadrant in the XY plane. But there are no other ways of traveling that stay within the plane other than combinations of up, down, left, and right. And because those come in pairs, up and down are opposites of each other. That's one dimension's worth of traveling. Left and right are opposites of each other. That's another dimension. We'll say that the plane is two-dimensional. There's a technical caveat we should make here, which is that a point is zero-dimensional, and there's nowhere to travel within it. Now, this isn't really useful because we won't be making measurements of points, whereas we'll start to try to measure length. That's a one-dimensional measurement. Area is a two-dimensional measurement. And then in 3 dimensions, like in the world we live, volume will be the right notion of measurement there. Points are just the degenerate case, you could call it. They're the simplest thing we worry about. They have 0 dimension. They don't have any room to wiggle around inside of the point, and there's nothing to measure with them. Sometimes they're called dimensionless particles or dimensionless quantities or objects by physicists, but we're not going to get into that. So here's a bit of visual intuition. We can measure objects of different dimensions, but the way that we have to measure might be different depending on the dimension. So the basic notion of measurement in this class, and there's a much more technical version of this if you go on and take more math classes, such as an analysis class. But in this class, what does it mean to measure an object or to make a measurement inside of some dimensional space? It means to count how many units of measurement fit inside of that object. And a unit is just, a unit also depends on what dimension you're in. For example, there are no units in a dimensionless object, a point, that has 0 dimensions and no directions to travel, so there's nothing to fit inside of there. In a one-dimensional object, such as this arc of a circle, we can ask how many line segments of length, 1 unit, fit inside of that total arc on the circle. Now, the way you do this, maybe back in, I think I might have learned this in middle school. I just have this hazy memory of measuring circular pieces with string. You might stretch out a string and cover the entire arc, and then take a scissors and chop either end, and then go lay that piece of string flat. That is the length of the arc then, and lay it flat against a ruler, and then read off how many units of measurement the string takes up. That's a physical way of measuring. But if we can't physically pick up this arc and essentially lay it flat, we want to find other ways of measuring its length. Arc length is something that we'll talk about at some point. Area is something we've already been doing, although we can ask the area question for more difficult 2-dimensional things. We could ask it for the XY plane, and that's the kind of area we've been working with so far. How many little squares of unit size, so 1 unit squared of area, fit inside of a given region is something we can ask in 2 dimensions. But why not make our lives even harder and take a 2-dimensional object like this saddle shape? This is something we'll study in multivariable calculus before too long. There are 2 different directions to travel on this saddle. You can travel sort of along the upward facing curve or along the downward facing curve. And that's pretty much it. Any other direction you want to travel, you can get by some combination of those 2. We can ask how many unit squares fit on this surface that has a notion of area. It's 2-dimensional. We can also take 3-dimensional things, pretend that this is a solid cylinder here. Maybe if we've zoomed in quite a bit on a length of copper wire and chopped it off, and we just want this particular solid cylinder, we could ask how many cubic unit squares, cubic unit cubes fit inside of this cylinder. So that would tell you about the volume. The idea is, depending on the dimension we're in, we first want to make sense of the dimension, and that tells us there's a natural choice of measurement, either length or area or volume in these 3 cases, and maybe beyond if we get there. And then we want to come up with a method, some strategy for computing that measurement, that length, that area, or that volume. Just to give things some actual names, length, area, and volume, these will be the official names for measurement in each of these dimensions. And we've seen a couple examples in each dimension so far. Here's a more complete list of objects or regions that possess a certain dimension. Here's some 1-dimensional figures that you might already be familiar with. Here's some 2-dimensional figures that I hope you're familiar with in general, but specifically in this class, we'll be trying to make measurements on these types of objects. And for the 2-dimensional ones, those will be area measurements. Finally, here's some 3-dimensional objects we can measure using volume. And by the way, this is a strict classification or a strict nomenclature. If we talk about a 2-dimensional object, it doesn't make sense to ask about its volume. Sometimes mathematicians will say that a square, a flat square in the XY plane, has 0 volume. And that actually does make sense if we think of volume, a 3-dimensional measurement, as having a length, a width, and a depth. Well, squares have a length and a width, but their depth is 0. They're flat in the plane. So it makes sense to say that these other objects in different dimensions have 0 volume. For the same reason, a line has only length, no width or depth. So it has both 0 volume and 0 area. But also, we probably won't say things like that unless it's relevant to the particular problem. So it doesn't really make sense to talk about the volume of something in higher dimension or the area of a 3-dimensional cube we can talk about the surface area, but that will have to be about the two-dimensional surface of the cube. So to get started, how do we compute volumes? We've done some area. We have to get around to, I'll go back to the picture. Like this saddle shape is something we could have computed the area of. We don't know how to yet, but we can at least discuss its area, how many unit squares fit inside of it. But we will have to develop some multivariable calculus techniques to even pose that question. For now, we're just going to leave that as is and figure out some volume measurements that we can make. Somehow going up in dimensions to dimension 3, but keeping things simple enough graphically will allow us to solve the problem just with single variable calculus. So if you'll remember back to the earliest days of learning about areas and volumes, you probably learned area is base times height. We've used that so far in writing down the area between two curves. For volume, you can think of it also as base times height, but the key feature here is with a three-dimensional measurement, we need 3 dimensions of measurement or of sort of quantity for it. So the base or the height has to be 2-dimensional. Let's say that the base is a 2-dimensional area, and then the height is an extra 1-dimensional line segment, for example. Or in 3 dimensions, we have a 2-dimensional base and a 1-dimensional height. For example, you can think of, for a prism, something that has mostly right angles in its full 3-dimensional shape. You can see there are some right angles everywhere, and we're not going to completely dive into what prism means versus some other word for a 3-dimensional region. But if we picture this as lying flat in the XY plane, and it has some area, then for us, prism will mean that we just take this area and we sort of puff it up vertically into the 3rd dimension. So we take that, you can start over here in the XY plane. You can see that triangle line down in the gray XY plane here, and you literally just sort of copy paste it infinitely many times until you hit a certain height that you like. That'll be a prism. So anything where we can take a 2-dimensional object, a region, and smear it into the 3rd dimension just by identical copies at each slice. Another way to say this is that a prism, when we divide it into unit cubes, and notice some of these will get chopped off, but we can chop those into smaller fractional unit cubes. We can make our units smaller, in other words. A prism can be divided into unit cubes. That's how we're going to compute its volume. And the key feature of a prism is that each of these unit cubes is stacked in a stack that lies over a single square of the right area, really of the same 2 dimensions as the sides of this unit cube. So let's get into that a little more. Well, to motivate things, we're not going to try to, we'll do a little bit of practice to build this intuition, but our goal in the end is not to solve geometry problems. We're not trying to rederive the area formula, or rather the volume formula for a wedge like that triangular prism. Rather, we want some interpretations of integral formulas that can be described as volumes of solids in the XYZ 3-dimensional space, but might have more interesting interpretations. For example, integrals are supposed to be areas under curves. However, in Calc 1, we learned that the one interpretation of an integral, namely the integral of a derivative or a rate of change, is the total change or the total displacement of that function over the interval of x values or time values in this case. So we can use our geometric intuition of areas and ultimately volumes built up this way to better understand rates of change. That's sort of the first goal. It turns out this goes pretty deep, and we'll hang on to this for a while in this class. Volume will allow us, and we're not going to do this right away again, we'll build some intuition first, but volume will allow us to understand rates of change better. So let's discuss cross sections. In the overview at the start of this lecture, I said that cross sections are the name of the game. So what is a cross section? If we have a solid 3-dimensional object and we take a plane and slice through that object, it says a transversal plane. All that means is we're going to slice essentially parallel or perpendicular to some axes. In this case, if the base of this pyramid is the XY plane, we are slicing parallel to the XY plane. And the resulting 2-dimensional shape, in this case, it looks like a square highlighted in aqua here, will be called a cross section of this 3-dimensional region. So again, a cross section is we take a 3-dimensional thing, we slice it with a 2-dimensional plane, and then we look at the intersection, that slice that pops out, and that's a 2-dimensional shape. That'll have an area. The whole point of cross sections is if we take enough cross sections, or really if we take all of the possible cross sections, slicing an object, in this case, it looks like we're slicing some curvy lump vertically, we can reconstruct the original object from its 2-dimensional slices or cross sections. On one hand, this is good for visual intuition. 2-dimensional things are easier to handle. We could look at a plot of all of these individually in 2 dimensions and understand them using all of our Calc 1 techniques, curve sketching and asymptotes and all the other good stuff, max and min. But also we can assemble them back into the 3-dimensional structure, and it gives a fuller picture of that 3-dimensional structure. So there's sort of a nice idea at play here that 3 dimensions, volume, seems a little intimidating. Why don't we reduce it in dimension by taking cross sections to something 2-dimensional that we feel more comfortable computing things, namely their areas. At the end of the day, we'll want to reassemble the area information in 2 dimensions back into 3 dimensions, into 3-dimensional volume computations, and that's going to be what we accomplish today. By the way, thinking of applications, if you've ever seen any sort of MRI scan or PET scan or any other hospital equipment that performs a scan of your body, for the most part, I'm pretty sure all of the time, although I'm not an expert in this, all of these different types of scanning equipment take cross sections of your body using different types of electromagnetic readings. So some of them pass X-rays, that's a type of electromagnetism, through your body, and then some surface on the other side of your body will capture that data and will interpret it some way. But it's computing a 2-dimensional cross section and assembling all of these cross sections from different angles. This is especially how MRIs work, back into a 3-dimensional model of your body using the information that's gleaned from different angles. So if you're interested in going to health sciences, anything healthcare related, and really the technology behind different types of scans, this is a good type of intuition to build in this class. So how can we actually compute the volume of a solid that's not a prism? Remember that a prism just has equal stacks of cubes above each point in the XY plane at the base. We didn't even talk about how to compute that volume. I'm going to leave it as an exercise, but just to quickly remind you, if a prism here's the volume formula that I didn't properly pay attention to at the time. The volume of a prism is just going to be whatever the area of that base is times the height. And the reason this works is that each of these squares fits the height number of times into this solid, and the number of squares that I have is just given by the area of the base. So there's an easy formula, easy-ish, as long as you know what the base looks like. Here, a triangle has its own area formula, which is nice. You can compute volumes of prisms that way. So how do we do it for non-prism solids? Here's a pyramid, for example. Maybe we go on a road trip or go on a field trip to Egypt, and we look at the Great Pyramids, or go to Mexico a little closer. We could road trip it then and look at certain structures that maybe we can simplify and model this way with a pyramid. We want to estimate the volume of one of these things. Well, the problem here is if you look at the base and then you look at the unit cubes that will stack on top of that, there are a different number of cubes lying over each square in the base, depending on which part of the pyramid we're looking at. So in the center, there are more cubes stacked up, whereas on the outer regions, there are less cubes stacked up. So we need a different approach to counting our unit cubes than just stacking them up equally. And here's the cross-sectional intuition that we've been trying to develop. What happens if we slice the pyramid, but instead of slicing it into 2-dimensional regions, let's slice into 3-dimensional prisms. We know the area formula for a prism. It's the area of the volume formula of a prism. It's the area of the base times the height. And then if we take enough of these small prisms and then shrink their size, shrink their heights down to 0, we'll actually be taking cross sections, reassembling them into the original shape, and then getting an approximation, but ultimately in the limit, an actual value for the volume of this region. And I'm going to skip deriving this for you. It's in the textbook and you can read more about it there. You can also look back at lecture 2.1 where we did a similar derivation for the area formula for the area between two curves. But here's the punchline for us. If we have a solid and we stick it in the XYZ three-dimensional space, but what we'll do is we'll put it perpendicular to the x-axis so that we can slice. Sorry, we'll put it along the x-axis so that we can take slices or cross sections that are perpendicular to the x-axis, just like in this picture here. These are vertical slices perpendicular to the horizontal x-axis. If each of the slices has area a of x, this is now a function of x, and the area might change depending on which x value we're at, then the volume of the whole solid will be given by an integral. It'll be the integral from a to b of capital A of x dx. Here, a and b are just the bounds on the x values that describe how far our figure stretches along the x-axis. And really, the use of this theorem is if we have some region we want the volume of, and we can put it into this form, we can draw it in a way that we're taking perpendicular slices, we're taking slices perpendicular to the x-axis to get our cross sections, and those cross section figures have an area formula we can write down as a function of x, then we'll know how to find the volume, and this is the idea. So we're going to do a few of these for practice. Before I switch over to my tablet and work this out with you, if you want to try this on your own, at least try drawing it on your own. Pause the video now and give it a shot. If you've done volume problems before, if many of them were rotation, but they weren't cross sections like this will be cross sections with right triangles as the cross sections. Try to sketch it out and see what your own intuition leads you to rather than just watching along. But I'm going to switch over now. And let's work this out together. So I've already drawn for you my artist's rendition of what's going on here. I didn't read the problem yet, but if we find a solid S, this will be a three-dimensional shape that we can line up along the x-axis running from x equals 2 to x equals 6 and slice it with cross sections. We'll slice it perpendicularly to the x-axis. So my slices are vertical here. Each of the slices is going to look like a right triangle. And depending on what x value I sliced at, the area of that right triangle will depend on that x value. So at the slice for x value x, the right triangle will have height 1 over x and base x squared. What I've done here is I've laid the bases flat in the xy plane. So each of these vertical blue strips here is one of the bases of a right triangle. The height is sort of jutting out a little bit, but I'll draw my right triangle so that the other leg all lines up along the x-axis. So these are actually sticking up off of the xy plane. This is a three-dimensional figure. And notice that if the heights are 1 over x, they're going to shrink as we get larger and larger x values. Whereas the bases will increase because they're growing by x squared. Notice I could have drawn this with the heights flat in the xy plane and the bases coming out at you in the third dimension. Then it would look like a different figure. And that's also a valid way to visualize this. So using our theorem, which said we should integrate from a to b the area formula for each cross section as a function of x, let's try to come up with the volume of this shape. So the first step is to find a of x, the cross section area. Each of these cross sections is a right triangle. And we know that a right triangle has area 1/2 base times height. And now we just need to read the statement of the problem to determine what base and height are as functions of x. So the base here is x squared. And the height of the triangle is 1 over x. And I'm going to simplify so that we can integrate in a moment. This simplifies to 1/2 times x. But in general, this is the procedure. Find a general formula for the area of each cross section. And the statement of the problem says it's a right triangle. We know what that area formula looks like. It's 1/2 base times height. And then dig in a little bit into the problem. See if you can figure out or deduce what the different measurements are as a function of x. Here, the base and the height. And actually, fun fact, the base and the height are each one-dimensional measurements of the line segments making up the legs of the triangle. We can assemble those into a two-dimensional measurement, 1/2 x. That's going to be the area of each of these triangles. So notice that even though the height legs that are coming out at us are getting smaller, the base legs are growing by x squared. So the areas, even though this shape appears to be getting thinner, the areas are actually growing fast enough. And this is not a good artist rendition. The areas are growing fast enough that as we move forward or towards larger and larger x values, the areas still get larger. So let's write down the volume formula. We know it's integrate from a to b. Here we'll integrate from 2 to 6 of the area formula, which we just derived, 1/2 x dx. And we can do this one together. We didn't do any integrals in the last lecture, so let's do one together today. Actually, I don't need to write the integral formula again. Let's use the fundamental theorem of calculus. I'm going to take some antiderivative of 1/2 x. That's going to be 1/4 x squared. And then I'm going to evaluate that at 6 and at 2 and subtract the results. And I'll use another line to do this. At 6, so I'm going to pull out a 1/4. At 6, I square it and get 36. At 2, I square it and get 4. So this is 32 over 4. And I believe that gives me 8 for my volume. So this three-dimensional figure, which was not a prism, it didn't have equal stacks at each piece in the base, but this figure has a volume of 8. We just determined that using calculus. So this is the true volume, and any prisms that we stuck in there with actual width to them would be an approximation to this true value of 8. All right, so let's go back to the slides. To solve this problem, what can we do next? Well, let's talk about a rotation problem. Again, if you've seen volume calculations in your calc class in the past, this is probably the type of problem you did. So I'm going to read it out loud and not switch over and show you the picture yet. This is a good time to pause if you have done these before and want to practice as a review. If you have not done them, I'm going to work it through, but you might try to do the same procedure that I just did. Make some drawing that helps you get some visual intuition in the problem. And afterwards, first find the formula for the area of each cross section. And notice the problem doesn't tell you anything about cross sections. We'll have to do a little bit of thinking here. And next, try to write down the volume. Once you have the cross-sectional area formula, it's pretty easy to jump to the volume. So here we go. Let's do it. Here's the picture, but let's find the volume of the region or of the solid where we take the region under the graph y equals 5 over x plus 1 between these two x values and rotate it around the x-axis. We'll definitely do this in class. I'll start from scratch and draw it for you in the way that I think about it. But just to save a bit of time, I've drawn the graph of y equals 5 over x plus 1. I don't know exactly everything about this without doing a bit of curve sketching, but I do know that it's decreasing. And I mean, it looks like a 1 over x graph, that hyperbola. So I'm going to draw it kind of like that. And I do know if I need that at 0, I plug in 0 and get 5. So, it's touching the axis up here at 5. But really, I'm only worried about values from 1 to 4. So it's some sort of concave up decreasing figure. If I just wanted the area under that curve, it would be this blue shaded region. But instead, I'm going to take that blue shaded region and rotate it about the x-axis. And here's the trick. Using our theorem from the slides, can we come up with the volume of the solid, treating it as a cross-sectional problem? So if I take a slice at any given x value, can you see what the slices look like? Each one of these slices is a circle, and it's a circle perpendicular to the x-axis. It's in 3 dimensions, and it has a 2-dimensional measurement. It has an area to it. So the cross-sectional area here is the area of a circle, which I think we all know and love, pi r squared, where r is the radius. Now, I've helpfully left these vertical blue strips in, which are coming from visualizing the region under this curve, the area under the curve, y equals 5 over x plus 1. But each of these is also playing the role of the radius of the circle. So pi r squared, each of those strips is just the height of the function, 5 over x plus 1. So in this case, pi times r squared is just pi times the function squared. And I'm going to simplify again because I'll need it in a moment. We'll have 25 pi times 1 over x plus 1 squared. If you want, pause now and try to do the next part on your own before I work it through for you. So here's a cross-sectional area formula. See if you can at least write down the integral, and then hopefully you know how to solve it. This one is a little more involved than our power rule in the last problem, but I'll do it all in a moment. So I'm going to scroll down just so I have a little more room to write, but there's our picture. To write down the volume, once we have the cross-sectional area figured out, it's actually pretty simple. We'll take the x values to integrate along. That's from 1 to 4, and that's actually given to us in the problem, luckily. So from 1 to 4, we're going to integrate this area formula, which is 25 pi times 1 over x plus 1 squared dx. Now, there are a few ways to integrate problems like this. This is a rational, I can pull out the 25 pi in a moment. This is a rational function, so it looks like 1 over x plus 1 quantity squared. You can probably try to do a partial fraction decomposition if you remember that technique, but I actually see a better way to do this, which is to make a u substitution. The thing in parentheses here, I'm going to call u, so that I'll just have 1 over u squared. That'll be a power rule integral if I can work the rest out. Du is pretty easy, it's just dx in this case. And then I'll have to worry about the two x bounds, they'll become u bounds, but we'll do that in a moment. So first of all, let's pull our 25 pi out till the end. Next, we need to integrate. We'll write the bounds in a moment, but here when we make the substitution, we'll get 1 over u squared du. And that's an integral, at least as an indefinite integral that we know how to solve. Again, we want to worry about the u bounds when we do a u substitution on a definite integral. So if x equals 1, we can go feed that into the u machine over here. If x is 1, that means u is 2. If x is 4, u is 5. Or another way to say this is that u just shifts all of our x values up by 1. So of course we shift from 1 to 4 all the way up to 2 to 5. Makes sense. Let's integrate this. So this is a power rule. This is really u to the negative 2. I'm going to do this all in one step. This will be keep the constant out front. This will be negative u to the negative 1, which is 1 over u. And I'm evaluating this all from 2 to 5. So let me quickly solve this to get a nicer looking answer. We always want to plug in and then I can simplify a bit. So it'll be 25. I'll have negative 1/5 and then minus negative, that'll be plus 1/2. You can common denominator this and you'll see you get 3/10 inside of the parentheses. And that times 25 pi is 75 pi over 10. I didn't use my calculator to find a numerical approximation, like a decimal approximation for this, but you can check it out and see, oh, that's interesting. What's the volume of this sort of truncated cylindrical cone, or not cylindrical, this truncated round cone. It's almost like part of a volcano, or really the whole volcano if we have a big old top up here. We could find volumes that way, as long as we can model things using this type of curve. So there we go. Second problem done. Good work. Let's keep moving. So here's actually not an artist rendition, but a computer rendition of the last problem we did. So this is a picture, a three-dimensional model of the solid obtained by rotating that graph about the x-axis in the previous problem. We will learn in your lab sections how to create visuals like this at some point. So stay tuned if you want to be able to create these yourself, but also you can use things like Wolfram Alpha or any graphing calculator to get some sort of visual intuition for this kind of thing. The main takeaway from the last problem that we worked and relating it to, for those of you that saw volume by rotation in a previous calc course, to relate this to cross sections, the main takeaway is that if we take the area under the graph of a function, rotate about the x-axis, the cross sections will be disks or circles of a given radius, that radius will just be the height of the function, so f of x, and the areas of each cross section will then be pi times f of x quantity squared. Then we can integrate that function, pi times f of x squared, over the desired range of x values and get our volume. Next, let's move away from rotation and try a slightly different problem. So let's suppose we have a solid, and I'll draw it for you in a moment, that has the following properties. So the base of the whole solid is actually itself a region under a graph. So this is a two-dimensional region in the xy plane between the x-axis, that's y equals 0, and the function y equals 4x minus x squared. The cross sections, if we slice this thing perpendicular to the x-axis, now are going to be trapezoids. One of the bases of the trapezoids will be in the xy plane according to that region that we just described. The other base will be twice as long, and the units are constant at the heights are constant 6 units of height. Let's find the volume. So while I'm switching over, if you want to pause the video and at least try to sketch this for yourself, give it a shot, build some visual intuition without me helping you out right away. And then if you can, try to write down the volume formula. At a minimum, it would help to pause right now if you weren't able to do that on your own, and try to remember or re-derive for yourself the area of a trapezoid that has a little base and a big base. So here's my sort of sloppy artist rendition of the problem. I drew the parabola. It's downward facing. It has its peak at 2, it turns out, but you'd have to do some calculus to figure that out. But it's downward facing, it's a parabola, and I can definitely read off the intersection points pretty easily because I can set this function equal to 0. So 4x minus x squared set equal to 0 is something that you can work out. You'll get 0 and 4 as the two intersection points, and it doesn't intersect the axis anywhere else in between. So there's our region. What does this look like? Well, I tried to draw this not so much to scale, but so that we can see everything all at once. You can imagine we're looking at a really sharp angle downwards, and just sort of glancing downward at these trapezoids. The base side, or the base, the smaller base of the trapezoid, is a slice inside of the region giving the base area. So that's going to have a height given by the function. The second base, the larger of the two bases, will have twice that. So once we know one of the bases, we know both. And then the height here is always going to be equal to 6 units. So let's try to figure out, oh, look, the volume's going to be 32. I already worked this out. I'm going to at least set things up, and then you'll be able to compute something afterwards and compare it to my answer. So the cross-sectional area, well, you have to remember the cross-section, the area of a trapezoid, it's always going to be 1/2 big height minus little height. Big. I wrote B for big, but I really meant B for base. So 1/2 big base minus little base times height. There are a couple ways to rederive this. Maybe the magic word is subtract one triangle from another triangle if you want to go work this out on your own. But this is the formula, where B is the big base. I'll even draw it here. And little b is the little base. And in our case, actually, this is the big base is twice the little base. So for us, this will be 1/2 2b minus b, 2 little b. I'll just do it. I'll write it all out. 2b minus b times h. And, well, let's see what we get. So 2b minus b, that's just b. And let's plug in b and h given by the problem. So the little base is the one lying inside of the plane here, and that's just given by the height of this function. So that's 4x minus x squared. The height then is constant 6 units, so we'll just plug in a 6, and I'll simplify one more step. I'll have 3 times 4x minus x squared. Let's write down the volume of this region. this three-dimensional solid. This is a good place to pause. And now that I've worked out the area, or maybe you already had this and you're just following along to check, but if you weren't able to work out the full integral formula already, pause now and try to write it down for yourself using what we just derived together. And I'm going to write it down. We're going to integrate it along the x-axis. The x values are from 0 to 4, just like we drew in the picture. And in general, you'd want to intersect some curves to find those x values, just like we practiced in the previous lecture. And then I'm just going to plug in the area formula. And that's it. And it turns out that this integral has a value of 32 if I didn't make any mistakes. If I did make a mistake, then it's your job to catch it and let me know. But I think this is right. And that tells us that the volume of this region is 32 cubic units, cubic centimeters or whatever it is in this particular problem. Great, so that's 3 different volume problems. All of them use cross-sectional area computations and the theorem that we learned in the lecture slides. Let's keep going. This is, by the way, a much better computational rendition of that last region. They drew the trapezoids a little differently here. So what's interesting, actually, I think a really interesting piece of this puzzle is that I can sort of shift these trapezoids over to make them symmetrical so that the angles are symmetric. You can think of that as a truncated a truncated isosceles triangle. So if I drew this a little more like I did on the tablet, the whole shape would be shifted a little bit to the left and would be more symmetric. And you'd see really this angle would be the same as this. These are much different. This is vertical now. That's some obtuse angle here. If we drew that solid, it would actually have the same volume as this one. And that's just because trapezoid area formulas just depend on the 2 bases and the height. It's a 1/2 base minus base times height formula. In any case, the main takeaway from this problem and what we've learned so far is that in many cases, if we can draw our figure so that part of the cross section lies in the xy plane, and even in this case, it is the height of a function in the xy plane, that was our smaller base, and then the rest of the area formula for the cross section is related to that somehow, then we can come up with an expression for a of x, the area of each cross section, just as a single function of x. If there are multiple different quantities floating around, we'll have to use some mathematical investigation, some intuition of our own to search around in the problem and relate everything to a single variable x and have a single variable integral. In some problems that won't be possible. For now, that's all we're going to give you to work with. But eventually we'll try to learn about how to use more variables, more independent variables, and still compute things like this. So I'm going to draw this, but not compute it for you. I'll leave most of this as an exercise, but what we can do is actually, I said we're not going to care about this so much in the long run, but for now, just to build some intuition, we can actually rederive volume formulas for familiar geometric shapes, like a pyramid, a 3-dimensional pyramid, using our calculus intuition, actually using an integral formula. So let's try to find the volume of a pyramid with square base of side length s and a height of h, whatever units those are. And I'm going to, again, I'm not going to completely solve this for you, but let's try to put ourselves into a situation where we can use our cross-sectional area approach. So if I have a pyramid, if you actually go back and look at one of the earlier slides in this lecture, you'll see the pyramid sliced. And the way we sliced it is we laid it perpendicularly, or we laid it parallel to the x-axis. I'm going to draw it like this. And then we sliced it into cross sections. And I'll do it this way. I don't want to draw too many. I'm just going to get a little lazy. I'll draw one more. Here we go. Okay. So the base, first of all, is a square, but in fact, all of these are squares if I slice the right way. But of course, the squares are getting smaller as we move down, or I guess move up the pyramid if the base is at the left. So what I want you to do now is think about how to write down a formula for each cross-sectional area. It's a square, so the area is side length squared, but we have to write it down as a function of x if we're going to use our cross-sectional area formula. So the hard part here, I think, is correctly writing down, and it should involve the two parameters s and h that we could change to get a different pyramid and have a single master formula for at the end of this problem. If you change those, if you write down the correct area formula, then you'll just integrate it from, well, it's also your job to figure out the x values to integrate over. So I'm going to leave that as an exercise. We can certainly talk about this in the live session. But that'll be the last problem we do for today. Let me just recap a few things for you at the end. So we've learned quite a bit, mostly intuition, but we can solve a fair amount of volume problems now. So first, to summarize in a question form, to get you to reflect on this a little, think about how a cross-section of a solid is produced. What does it mean to take a cross-section? The original definition is some abstract mathematical thing, but it's helpful to keep this in mind, at least visually, when you're approaching a new problem. Next, what is the significance of the area function, a of x, in the formula for the volume of a solid? What shapes do we use to approximate the volume of a solid without using integrals, just to find the volume of a three-dimensional solid? What shapes would we use to try to approximate that? And why do we choose that shape? We didn't talk about this today, but why do you think that that's the right shape to approximate with? And finally, if we go back to some people's previous calc experience, for some people this is completely new, but when we find the region obtained by rotating some area under a graph around an axis, if we want to use our cross-sectional approach to recover that formula, how do we compute the areas of cross-sections in that setup? Here are 4 practice problems that I'll leave as exercises at the end of this video. And again, you can find these slides on Canvas, and I encourage you to try, at least think about setting up each of these 4 problems. Here's the second one. Here's the third one. And here's the last one. All right, thanks for tuning in. That was lecture 2.2. I'll see you next time.